Hi, everyone. Thanks for coming right after lunch. I know that was a big meal, standing outside in the sun. I haven't fully digested everything, so this could be a little dicey. We'll see. So I'm John Feminella. I'm an advisor for a company called Pivotal. Pivotal actually just went public about 3.5 weeks ago, which is very exciting for me. But in the course of my job at Pivotal, one of the things that I encounter is working with these really large institutions, large finance companies, banks, hospitals, et cetera. They build their applications a certain way, and they want to measure and understand the health of those applications in a certain way. And I started seeing this pattern kind of regardless of what size the application was, what size the company was, what size the team was. And I think that there are some improvements we can make in how we monitor and measure our applications that requires a little bit of a shift in our philosophy, which I'd like to talk about today. One logistical note, at the end of this talk, I'll make sure that we have time for Q&A, but at the bottom of every slide, like there is at the bottom of this slide, is also my Twitter handle. If you reply to the latest tweet on my page with any questions you have during the talk, I'll make sure I get through those first, so you don't have to remember the question all the way through the rest of the talk. All right, so let's get started. Now, when we want to understand the health of a system, there are a lot of things we could measure about that system. So we, for example, could pick how much CPU usage there is, or how much memory usage there is, or the amount of disk I/O, and so on. And in fact, because it's gotten, because of various improvements to Moore's law and how cheap computing resources have gotten, it may even be really inexpensive to measure things today as compared to, say, 10 or 20 years ago. And it's not that expensive to measure those kinds of things either. That is, it's not only cheaper to measure each individual thing, but it's also cheaper to store the metrics over time. So you can, for the same amount of money that you might have spent 20 years ago, you can take a look at a much longer period with a much higher granularity of the metrics that you might have otherwise wanted to measure. So to take a concrete example, let's say that this system is one of many instances in a larger distributed system. And let's say that we measure 100 different data points for 100 different kinds of data, 100 different metrics, which we'll call streams, for this particular instance. So a stream in this case would be, say, the percentage of CPU usage, or the number of gigabytes of memory being used, and so on. So each one of those is a separate stream. So let's say that we want to measure 100 such streams, so not just CPU, memory, or disk I/O, but 97 additional things that we'd like to measure about that application. And let's say that we measure each of those values. We sample them at 1 second for each stream. So every second, we're measuring the value of that particular metric. And let's say that we allocate 24 bytes for each sample. So that's a fairly large amount. That's enough for 8 bytes for a timestamp, which is what we use for 64-bit timestamps. That's 8 bytes for some kind of identifier, and then another 8 bytes for the actual value of the metric. So that's a lot of. That's usually pretty substantive. That's pretty generous in terms of the amount of data we would allocate for a given metric. So if you do the math on that, you wind up with 2,400 bytes per second per instance. And then if you say that there are 100 such instances in this distributed system like we did before, that's 240,000 bytes every second, which is about 7.5 terabytes over the course of a year worth of data, worth of metrics. Now, 7.5 terabytes might sound like a lot for one of your hard drives, but if you want to store that in the cloud, that's extremely cheap to do that today. For the cost of about $200 US, you can store that in Amazon S3 for the whole year. So every year you'd be paying that amount if you wanted a 1-year data retention window. So if you're an enterprise like a bank or a hospital, $200 on top of your application cost is nothing. So you might say, well, if we can measure everything, why wouldn't we want to measure everything? Why wouldn't we want to measure as many different data points as we possibly could for as long as we possibly could, so that we understand everything there is to understand about our application? This seems like an objectively better reality as compared to a situation where we store fewer metrics. So why wouldn't we want to store as many data points as possible for as long as possible? So you might say, well, you should. That is the right thing to do. You should store as many data points as you can, because if there's ever a problem, you will know how to solve that problem by looking at when the problem has occurred in the past and seeing, oh, what does this pattern look like? And does that pattern match previous instantiations of this pattern? And if it does, if you have a long memory because you've been storing lots of history about your app and its metrics, then you will be more likely to be able to solve those problems more quickly. Or so that is the reasoning that many people use and many companies use for why they should store lots of stuff for long periods of time. But there arises a very specific question, which is, are you actually measuring the right thing? So who's to say that the 100 different data points, the 100 different streams that you were measuring, who's to say that those were the right things to measure? What if there is a 101st metric that was actually highly correlated with the health of your application that you didn't pick? So I would argue that it's not about how much you measure, but what you measure, and the degree to which that correlates with your understanding of the application's health. And people who look at this from an observability perspective, from the lens of the application's health and providing that application as a service to others, they say that there are three kinds of ways to think about that statement of whether or not the application is healthy. So the first statement is something called an SLI, a service level indicator. It's a promise that we're going to make to people who consume the application, who depend on it in some way. So this is a statement like, I should be able to log into my bank account, or I should be able to post a tweet, or I should be able to, whatever the definition of what it means for that application to be doing its job is, that's the promise we want to make. That's the service level indicator. Then there's the service level objective, which is the notion of how true or how frequently or how intense the promise is, how strong is the promise we're making. A statement like, you'll be able to tweet with no more than 0.1% downtime is a stronger statement than you'll be able to tweet with no more than 1% downtime, right? Because we're making a stronger promise about the availability of that system. And then finally, the service level agreement is what happens when the promise is broken. So if we don't maintain that availability number, what happens? Do I owe you some money because I breached a contract? Do I remediate the problem in some other way? So for example, if you have an internet service provider and you're a residential customer, you probably don't have an SLA. Your internet service provider just says, well, I'm going to offer some internet and you take it or leave it, as it may be up, it may be down, but I'm not going to make any specific promises about whether or not it's up or down. And in addition, if it's down, I'm also not going to give you anything for it being down. Maybe you get a refund for that day that it was down or something. But if you're a commercial customer who depends on that internet service, you might have a much stronger contract that says, hey, when we go down, we'll pay you $1,000 per day because you were down. Now, so if we take these promises that we'd like to make about our application and we want to codify them into a statement about what it means for our application to be up, maybe this is a better way of understanding what metrics to pick from than trying to just measure everything or as many things as possible. The problem with this approach is that humans are really prone to different kinds of mistakes and biases. So for example, maybe you've seen this math equation. It's called Euler's identity. And mathematicians like to think of this as very beautiful, that it unifies these 5 different constants, e, I, the imaginary unit, pi, 1, and 0, all very important mathematical constants. It unifies them into one equation. So that sort of elegance, or that apparent elegance, seems very beautiful to some people. And I think inherently we have this belief that, well, if something is simple or if something is sort of compact in this way, then it's necessarily good. It's better than a more complicated version of the same reality. And as humans, we've been evolutionarily predisposed to being able to make quick decisions. If you see the face of a predator, you have to be able to understand whether or not that thing might want to eat you and whether you should fight it or run away from it or do something else in a very short amount of time, because if you don't, you might get eaten. And so this predisposition to wanting simple answers, simple packaged sort of ideas, no matter how complex the underlying domain is or the underlying problem is, has been something that I think has stuck with us for a while. So, for example, even when we're not talking about complex systems, if we're just talking about, say, the weather, if you look back at the history of how we try to explain complex phenomena, one of the major cultural things that's happened in many different cultures is trying to come up with explanations for floods, for famine, for storms, for large-scale things that seem to happen to everybody, but that are difficult to explain if you don't know how ecology works or weather works and so on, right? Which is why if you look at across many different cultures, there's very consistent there are many deities that all have the same portfolio. So, for example, here's the equivalent of the god of thunder or the god of storms, a deity that's responsible for this complex system like a thunderstorm, but has a simple explanation. Oh, a deity did that. Jupiter is the one who sent the storms to us, not this complex system of wind and rain, right? So there are lots and lots of examples of this throughout history where we want a simple explanation for a complex problem, but we don't know all of the underlying information, so the best we can do is invent what we think is the best explanation at the time, which for many cases was a deity. But as our knowledge about the world increased, we didn't necessarily need to rely on an explanation like, Jupiter created storms. We started understanding, storms are actually created because of physical interactions between the water cycle and hot air and cold air mixing together and so on. And this approach really started to take off in the Enlightenment era in Europe in the middle of the last millennium. And one way that people tried to reason about these complex distributed systems was to look for places where science and nature could intersect to make humans' lives better. So they were looking for places where they could apply, say, their knowledge of how to grow better crops to make farmers' lives easier and produce more food for the same amount of work. That's a net improvement in everyone's quality of life. So effectively, what these people were doing is wondering how can they optimize for the effectiveness of some system over some period of time. And they wanted to effectively control this distributed system. In the 17th and 18th centuries, a few countries got really interested in this fusion of nature and science. At the time, it was common for the governments of Europe to own large tracts of state-owned forests. So you had basically like the king's forest or a forest that was controlled by the crown or the monarchy or the government at large. And it was not available for use by farmers. So it was owned as a sort of strategic national resource, the way that companies today might hold on to barrels of oil. That's the equivalent, but with wood in the 16th and 17th century. And so they started wondering, this is an important natural resource. How could I optimize for how much timber I might get from this resource? At the time, timber was really important for making ships, for going to war, for building forts, for all kinds of military and civilian uses. And so the ability of your country to deliver high-yield timber at a high rate was effectively the bottleneck on how much military might you could deploy at any one time. So if your forests weren't that good, if you weren't optimizing as much as your next door neighbor was, then maybe for the same amount of land, they could come invade you because their forests were higher yield and they could build more ships or build more forts and so on. So this is a very important natural resource that it was very important to optimize for. So a number of states were very interested in this, but two particular states, Saxony and Prussia, got very interested in this idea of scientific forestry. They sort of wanted to apply science to how forests were grown, how forests were built, and how they were deployed en masse within these state-controlled enclaves. So Saxony and Prussia don't exist anymore. They're basically now part of what you would consider modern-day Germany. And they were sort of the first two pioneers in this area. And so they started wondering, is it possible to optimize the output of the forest? Now they knew at that time that some trees were better than others for shipbuilding or for houses or for forts. They had stronger wood, they had more dense fibers, and so on. And so they said, well, it seems like the first step you could do to optimize this would be to look at the yields of wood that you get from each kind of tree that's in our forest. And then you find the best one, and then you just plant a lot of that tree and chop down the other trees that aren't the best tree. And then if we sort of run experiments for all of the trees that we have that are of that really good high quality yield, it turns out that this is a particular tree called the Norwegian spruce, was the best highest yielding timber at the time. So they planted a lot of these Norwegian spruce trees, and they said, let's try running experiments on each collection of Norwegian spruce trees. Maybe this one we'll plant them a little bit closer. Maybe in this section we'll add a little bit more fertilizer and a little bit more water. Maybe in this section we'll prune the trees a little bit. And then we'll keep running these experiments over and over and over again until we find the most optimal tree yield for the Norwegian spruce. So that's what they did. And it turns out that this worked really, really well for the first generation of trees. They found the best kind of tree. They found the best combination of variables that optimized for the health of that tree, and then the trees grew really, really fast. And so Saxony and Prussia were like, wow, this is amazing. We're growing trees at 350% better yield than we ever had with the state-owned forests. Everyone who isn't doing this is effectively a state secret now, because if we can keep this to ourselves, then we'll be able to go out and invade other countries, because our forests are much more valuable, and this secret is much more valuable than somebody who's not curating their trees in this way. The problem was that the second generation of trees did much, much worse. And what they didn't realize, because they didn't know at the time, was that the supporting ecology of the forest, all of the other trees, all of the animals that lived in those trees, all of the underbrush of the forest, all of that was gone, because they basically replaced it with this sterile sort of long rows of trees in straight lines sort of approach. So it looked much nicer and it was easier to work with, but it wasn't really a forest anymore. It was more like a lab in which they were trying to grow a forest. So the nutrients that needed to exist for the Norwegian spruce the second time around didn't exist anymore. So those second generation of trees didn't have anything to eat, so they didn't grow as much as the original generation did. So arguably, they missed the forest for the trees, to use a metaphor. So they didn't understand that there was more to the story than just what they could measure, or what they thought was important to measure. And even though they were measuring lots and lots of different variables, they weren't necessarily measuring the right things. And by the time they realized that they should be measuring those things, it was too late. The forest was dead, and it took about 100 years to recover. The second problem with this kind of measure everything approach is that humans not only are sort of prone to these simple explanations for complex phenomena bias, but we also have actual visual quirks in our system. So I'm going to invite everyone to maybe just be careful of your neighbor, but if you put your hands behind your head and interlock your fingers so that they're touching each other, kind of like you're leaning back in a chair, so try that out. Any place that your fingers are touching, that's about where a part of your brain called the visual cortex is. You can put your hands down now. So any part that's kind of at the back, right above where your neck is, that's roughly where your visual cortex is. And that's the part of your brain that controls and controls your vision and tries to make sense of what you're seeing at any given moment. So we're going to try a quick exercise. I'm going to show you a number of dots on the screen for about 350 milliseconds, and your job will be to count the number of dots that you see in that amount of time. So we'll start with an easy one. So I'm going to ask you how many dots there are in the screen. All right, so raise your hand if you thought there was 1 dot, 2 dots, 3 dots, 4 dots. Okay, yeah, there were 3 dots that time. Let's try a slightly higher number of dots. Raise your hand if you thought there were 4 dots, 5 dots, 6 dots, 7 dots. Okay, so a little bit more dispersion around that time. So there were 5 dots in that case. Let's try one more time. Okay, raise your hand if you thought there were 6 dots, 7 dots, 8 dots, 9 dots. Yeah, way more dispersion, right? It turns out there are 8 dots. And the reason that, don't worry, I don't think any less of you if you didn't get the right answers. And the reason that there's more dispersion, the higher the numbers go, is that you're able to actually count instantaneously groups of things that are smaller than about 7 plus or minus 2. So if you have about 7 things, you're not actually counting the things individually. You're doing something called subitizing. You're recognizing at a glance how many things there are without needing to individually label the things. Once it gets above that threshold, you start needing to individually label the things. Humans use numbers, so we would say 1, 2, 3, 4, but you could just as easily label them with apple, banana, carrot, and so on. It would just be different. You're applying a label to each thing. That's enumeration. And it turns out that our visual cortex is optimized for about 6 or 7 things at a glance. Once we start getting above that threshold, we have to start using enumeration rather than subitizing. Another sort of visual quirk is maybe you've seen this optical illusion where the square marked A and the square marked B are actually exactly the same color. That seems crazy or really difficult to believe. Here's a bar that's the same color that connects both of them to prove that it is in fact the same color. So if you don't have the bar there, though, that visual illusion is really strong. It seems like A and B can't possibly be the same color, but again, they are exactly the same color. Or maybe you've seen this illusion where there are 12 black dots at the intersections of these lines. And if you look at maybe one, or you can probably see 1 or 2 at a time if you look really specifically at that intersection. But it's really hard to see all 12 dots at the same time, and you probably can't see more than 3 at once. And that's because the resolution of your vision is very limited for anything you're not staring directly at. So you basically have really high resolution for whatever you're looking directly at, but you have a very sharp resolution fall off once you get to the periphery of your vision. And your brain is effectively, your visual cortex is filling in details for you about what it thinks is there, but it's not really there, which is why you can look at one dot and see that. You can look at all 12 dots individually, but you can't see all 12 at the same time. If I reduce the contrast, or if I increase the contrast between the background and the dots, it's probably a little bit easier to see more of the dots at once now because we're taking advantage of the fact, or we're recognizing that you have lower resolution, so we're making it easier to see the dots. So now you can probably see more of the dots than you could before. Another kind of weird quirk we have is something called apophenia, which is a tendency to see patterns or recognize things where there are no patterns or that isn't really an instance of a thing. So for example, this might look like a face, but it's not a face. This looks like it maybe has 2 eyes and a mouth, but if your face looked like that, that would be a very serious medical condition, and your doctor would be probably concerned for your well-being. And similarly, these are just pictures of electrical outlets with stickers that you can buy on Amazon to put on. These are US electrical outlets. But if you can buy stickers to make these look like a face, right? But again, these are not faces, right? These are just electrical outlets with stickers on them. And similarly, when we see patterns of data, so this is basically some mostly random data that's been perturbed very slightly. And it has some statistics, so it has a certain X bar, it has a certain Y bar, it has a certain standard deviation with respect to X and a certain standard deviation with respect to Y, and it also has a certain correlation. So these 5 statistical values for that graph, for that data set. Now, that same data set, this same set of statistics is also true for this data set. This is a dinosaur. These are the same data points that have been perturbed to resemble a dinosaur. They have exactly the same statistical values. So both of these graphs have exactly the same statistics, but exactly the same statistics, but they look very different from each other. So if you were looking at, say, how much CPU usage or memory usage or whatever, and all you had was those values, you can't really tell whether the thing you're looking at is a dinosaur or some random noise. And so here's a quick animation of the same data set being perturbed into many, many, many different structures gently, moving one point at a time so we don't upset the statistics too much. But you can see that although the although the sort of we're moving things around such that the least significant digits are changing on these statistics, but the most significant digits are not changing. So we can do that. We can perturb these data sets in such a way that we can have radically different stories that we're telling about the data, but yet the numbers that we're measuring are the same. So you can imagine that in a world where this wasn't the mean of the value, but instead was representing memory usage or CPU usage or disk I/O, this isn't really enough to tell you how much, whether or not your application is healthy or what the underlying story is. So we have kind of a fundamental mismatch here where we have this objective objective reality that we want to measure, and it has to get interpreted through this subjective lens of our vision and our analytical processes and so on. And it turns out that we're good at making lots of data. We're good at building these systems that can churn out hundreds of different streams that we could choose from, but we're terrible at analyzing all of that data. We couldn't even see 12 dots on a screen, much less try to understand like 100 different data streams, like in our earlier example at the very beginning. So I like to say that we're good at big data, but we're bad at fast data. We're bad at analyzing and understanding the data that we generate. So that means in a world where we have lots of things like memory, CPU, and disk I/O, and other metrics like that, the sort of low-level details, and in a world where it's cheap to make those things and generate that data set, that has to compete with very expensive uses of our attention, of our ability to analyze and understand that data. And I like this quote from Herbert Simon, who wrote a book called Designing Organizations for an Information-Rich World, not in 2001 or 1991, but in 1971. He said that in an information-rich world, the wealth of information, so if you have a lot of information, that means a scarcity of whatever it is the information consumes. And what does information consume? Well, when you have a lot of information, what it consumes is your attention. So imagine your phone, right? If you get 500 notifications a day and you're checking it constantly, you're probably not paying attention to whatever else is happening around you. So you have a limited amount of attention to draw from, and the more the more you spend that on things like memory, CPU, disk I/O that don't correlate directly with the health of your application, that's competing for the things you probably really do care about, like is this application alive in a way that I care about? So my proposal is that we optimize for the attention that a human would have to pay to the application. And I think the way that we do that in a real system, my proposal for the way we do that in a real system is this. Let's say that you're considering some distributed system. And real-world distributed systems are messy. They have many different topologies. They have many different patterns and ways that they could be organized. But when you look at like the dashboard that's supposed to monitor that system, it never looks like this. It always looks, really neat and orderly with boxes and grids of graphs and charts. So there's something seems to be lost there that's not really capturing the essence of what the system is. Because, that doesn't look anything, the thing on the left doesn't look anything like the thing on the right. But what we're saying is, well, we should measure all of those things the same way. They should all be measured like that, even though each part of the system has a completely different responsibility and is doing a completely different thing, we're measuring the same stuff about all of those parts of the system. That seems a little weird. So I think the way that we get to a world where we are optimizing for attention is that we embrace the fact that these things are different from each other. It's not appropriate or correct to paper over those distinctions. We have to embrace the fact that they are, in fact, different. You have to embrace the inherent complexity of you deploying 1,000 different applications to your Kubernetes cluster. That is 1,000 different things. You can't measure those 1,000 different things in exactly the same way. You can't have one metric story for all of those thousands of different things. So in a world where that's true, if we agree that we shouldn't measure all of those things in exactly the same way, how should we measure each different component or each different application? So let's say that we have a system like we did at the very beginning of the talk, and we don't know anything about the system itself. We know maybe it's an app, but we don't know what's inside of it or whether it's got 5 databases and a web framework and some back-end microservices. Whatever is inside of there, we don't know that. So it could be really simple or it could be really complex with a bunch of different moving pieces. It doesn't matter. We just have this sort of black box view of the system. What should we measure about this system? If we could ask any question we wanted about the system, What should we measure to understand the health of the system? So I think for that, we need a different sort of metric. And I think the metric that I would use is this, or the set of metrics I would use is this. It's actually 4 different metrics, or 4 different pieces of an overall story. The first piece is the demand on this system. How much work is the system being asked to do? What does work means? It means whatever the system is being asked to do, whatever that unit of work is. If you sell concert tickets, then it's probably the people buying concert tickets on your website. If you are a patient portal for a hospital, you're probably the unit of work is a patient record. Whatever that unit of work is for your system, or sets of units of work for your system, that's the demand. That's the kind of work that the system is being asked to do. The second question that we want to ask is, how much of that demand is being satisfied? How much of the work that we're being asked to do is getting done within our SLIs and SLOs? So how much of that work is actually happening? So if we get 1,000 queries per second, but we're only processing 800 of them within the SLO, then we're dropping to 20% of the queries that we should be processing within the SLO on the floor. That means we're failing in some measure. The third thing we want to ask is about efficiency. How well are we using the computational resources for the system to provide output? Excuse me. So the resources that we were measuring before, like memory, CPU, disk I/O, we still want to measure those things, but those things they're not the first-class citizens of this story. They're an input into understanding how efficiently the system is consuming or using resources. And then finally, the last piece of this is capacity. Does the system have enough of those computational resources to do the work that we're demanding that should get done? So this is sort of this is a very different picture than measuring CPU, memory, disk I/O all by itself. This is a much higher level idea, and specifically the trade-off that you have to make if you want to work in this approach is that you have to actually understand the system, or somebody has to understand the system. Somebody has to be able to say, this is what it means for the system to be doing work. This system processes checks, or it curates insurance policies, or it helps you buy concert tickets, or whatever. It can't be an abstract line item in the list of applications in your Kubernetes pods, right? It has to be something where you understand the application. So that means you can't treat every application or every component of your distributed system identically. They have to be treated differently. And not only do they have to be treated differently, they have to be treated in such a way that somebody specifically understands the difference between all of them. So let's look at some specific examples of this that are in the real world from folks who have applied this methodology. So in this particular Kubernetes cluster, there is a database there's a set of databases that serves all of the applications in that cluster. They're all related in various ways, and they all depend on access to this data set. So the operators of this system decided that the way to measure the work that was being done by the system is how many queries does this database receive, and how many of those queries do we process within our SLA. For a US concert ticketing website that gets about 10,000 requests a minute during popular ticket sales, they decided that the way they were going to measure the work done by their system was, hey, the number of requests we get to reserve or buy a ticket as compared to the number of purchase experiences people get without negative user experience, so the number of positive purchase experiences. And for a third example here is for a hospital that services about 1,000 patients at a time and has an electronic medical records or EMR system that doctors and nurses use to fetch the data. So they said, hey, well, what we're going to measure in terms of work being done by the system is how many patient record requests are we getting, and how many patient record requests are we returning. So we have that story-based approach, but what we don't necessarily have is tooling that supports this. And if you look at a lot of the tooling that we have today, we have the way that you can check if you're in line or not with one or more of your metrics is you set a threshold in general. You say, hey, alert me when memory is above 90%, or alert me when CPU usage is above the 85th percentile or whatever. That doesn't work so well for various reasons, though. So let's look at this graph of CPU usage over time. And this graph has a number of spikes in it. And we could say, hey, you know what? We want to set a threshold here. And then if we ever get above this line, I want you to send me an alert. So in the future, we'll miss this spike and that spike and that spike, but we'll catch this one. So maybe like we have an outage and we say, oh man, that outage sucked. I hope that never happens again. Somebody should set a CPU alerting threshold so that when the CPU goes haywire, we get an alert that says, hey, check on this system, something's wrong. So if we set the threshold there, we'll miss every subsequent spike. So now if this represents another outage, we'll say, oh man, okay, well that was like we missed that, like that's a problem. We should set the threshold a little bit lower. But the problem is, like, no matter where you set this threshold, it's an arbitrary choice. It requires you to know something about the future. It requires you to predict the future about what the right number is for CPU usage for this application in terms of whether or not the application is healthy. And I think that that's not the right way to do it, because that's just a guess about whether or not the CPU usage threshold is correct. And you probably, if you do it this way, you probably get lots of false alerts when the CPU usage is high, but there's no actual problem with the application. So I think a better way to do this is to look at, for each metric that you care about, look at the sample that metric over time. And you'll probably get a few outliers in the samples, and you'll probably get a large bulk of data that represents some normal range in which the system typically operates. And now if you sort those points from the lowest to the highest, you'll see very clearly, like, hey, there's this range in which the system's behavior is mostly consistent, mostly linear. And then there are these tails at the end where the system doesn't really behave like we want. It consumes exponential amounts of resources as compared to the demand that it's getting. So if we zoom in on that, we can see, hey, there's like this kink in the graph here, right about it being 99th percentile. That's where the behavior of the system seems to change. So if you're going to set a threshold, that would be where you'd set the threshold, right there, not at a guess like, oh, 90% is where I should set the value of this threshold alert. So if you use those two pieces to create a story to understand the raw data, you can do a little bit better than you might have to do otherwise. So for example, let's take these three scenarios where we look at we have some database system, and we're looking at the queries it's processing versus the queries it's receiving. Let's take one scenario in which we get a load spike. So the number of queries we receive goes up by 20%, and the number of queries we process goes up by 20%, and the amount of resources we used also went up by 20%. Should I send an alert in this situation? Raise your hand if you think you should send an alert. Raise your hand if you think you shouldn't send an alert. Right, you shouldn't send an alert here, even though you had a load spike, because the system is still operating normally. The efficiency is the same, and the usage is proportional to the amount of resources, to the amount of demand that you have. Right, if you have a lot of memory and you're using more, if you have a certain amount of memory and you're using twice as much memory as you were before, that's not necessarily something to alert about if the amount of demand also went up by twice as much, right? Like if you are servicing twice as many people at the same time, you probably expect to be using twice as many resources. So again, I don't think we would alert in a situation like this. What about this situation where the resource usage goes up? So we have lower efficiency. The queries the queries again are up by 20%, and so are so demand is up by 20%, so is the output, but the usage is up by more than that, right? Now here we probably should alert because our efficiency went down. We're probably entering that region of the graph where we're sort of in an exponential growth rate. So that's a case where we probably should alert our operators that something is amiss. And finally, what about this scenario where the demand is rising over time? So our queries went up by 20%, but our output only went up by 5%. Should I alert in this situation? Raise your hand if you think you should send an alert. Raise your hand if you think you shouldn't send an alert. Oh, okay. a lot more 50-50. So I think that you should send an alert in this case because even though the efficiency is the same as it was before, you are not servicing all of the demand that's coming in. So you're dropping some of these queries that you would have been processing on the floor. So I think that this represents a situation that you'd want to know about. Now again, other metrics are important too. You still want to know about memory, CPU, disk I/O, but that's not the first thing you look at to understand whether or not the system is healthy. I think what you look at is this story of the demand versus the output and the efficiency and the capacity. So again, other metrics are important too, but I think that focusing on those four for each application or each component of your distributed system is the right way to go about it. Now, before I said that this came with a cost, that you have to understand more about the system than you might otherwise have to. So you might wonder, is it worth it to do that? So 3 Fortune 100 firms that I work with, they have tried this approach. And here are some of the things that they saw. They saw a mean 98% reduction in the false positive rate. So in other words, if you were getting 500 pager duty alerts, you are now getting 98% fewer alerts. You're getting 225? Wait, no, you're getting 10, 20. You're getting 20 different alerts instead of 500. It seems like a win. They saw a 1,500% improvement in correlated outcomes. That is, when they got an alert, it was much more likely to be an actual problem than something, something just buzzing and saying, oh, hey, we had, your memory usage is above 95%. Here it's actually representing a real problem that people needed to deal with. And then maybe even more tellingly, all 3 of these firms have expanded this approach to new systems that they're building, as well as investing to expand it on systems that already exist. So if I leave you with 3 takeaways, it's that you want to put humans first when we're measuring and monitoring these applications. Humans are scarce and expensive. Data is cheap and plentiful. Attention, your attention, the people who are responsible for making decisions about these systems, is the scarcest computational resource of all. So don't optimize for memory, CPU, or disk I/O, optimize for your attention. There's always more data that you could be generating, always more things you could be measuring. There's almost never enough attention to go around. So if you optimize for that, I think you'll be happier. Thank you very much, and I'm going to pop over to my questions now.